The next item here, we are to find the number of n-digit quaternary sequences that contain an odd number of zeros, an even number of ones, and at least one 3. Take note and don't forget that quaternary sequences are sequences using the digits 0, 1, 2, and 3. So there are 4 different objects here, but it's very strict that for n-digit, we don't know how many digits are there, but for n-digit quaternary sequences, the number of zeros are odd, number if even are ones, and there is at least 1 3. We don't have a restriction for our 2. To do this, understanding that first, whether which will be used, ordinary or exponential generating function, we're going to use actually here the exponential since we're talking about a set of sequences. Okay, say for example 0, 1, 2, 1 and 1, 0, 2, 1 are different things if we talk about sequences. In short, order here doesn't matter. Order here matters. They are counted differently. In short, instead of ordinary generating function, specifically, we're going to use here the exponential generating function. And for that, let's try to identify the equivalent generating function in terms of exponential generating function for each specific item. For 0, since they're odd number, that means we're going to consider the item that so we only pick the odd existence. That would mean we will no longer write 1 because 1 is not odd. It's just an opportunity for not to be existent. So we don't need to write that. What we need to write here is to start from x. And of course, since we're talking about exponential function, it's x over 1 factorial. Plus, we don't need to write x squared over 2 factorial because then again, we are talking about odd. So we jump into x cubed over 3 factorial, then x to the power of 5 over 5 factorial, plus so on and so forth. That's for our digit 0. For our digit 1, even number, so we're going to pick the opposite of 0, but we count here 1 because 1 sometimes is considered to be non-existent, is already there. So we will have here plus x squared over 2 factorial plus x to the power of 4 over 4 factorial, and so on and so forth. Now, for digit 2, okay, let me write it here. Digit 2 has no restriction, so we simply write all the terms 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so forth. Now, for digit 3, at least 1. That would mean it is a guarantee that 3 is already in the mix. So I would like to add this opportunity here. I'm going to add 3. So it's already a guarantee that 3 is present. And then there are, of course, I'm going to remove this so that we will not be confused with what we need to use. So since we're talking about at least 1, like this 1 here, the term 1 is not in this in its exponential generating function because 1 stands for the possibility of non-existence. So here we have here x to the power of 1, x to the power of 1, right, over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus so on and so forth. Now, these are the 4 exponential generating function assigned for each digit together with its condition, and then we just simply to multiply them to identify the a sub n x to the power of n over n factorial. If we could find this expression, okay, what is this? Is our result for a general formula, because we don't know the number of n in this case. So general formula for this type of situation. Okay, but when can we get that? We can actually get that using this identity: e to the power of x is equal to the summation of x to the n over n factorial as n starts from 0 to positive infinity. Take note, we are using n. We have been using r in some instances, but here we're using n because n is identified here as the variable as well. So we are going to express all of these 4 and even their products in terms of e to the power of any term. So to start with this here, for odd numbers, we actually already have the formula for that. For odd, we actually have this formula, e to the power of x, not formula, identity, we have previously proven as well. E to the x minus e to the minus x over 2. Okay? That is for odd selections. For even selections, we also have another identity for that, already proven as well. So simply use that. It's actually e to the x even, okay, for 1 even, plus e to the power minus x over 2. Okay. just for that portion right now. Now, for the digit 2, there are no restrictions. So we simply copy this one here. I'm talking about this one here. We're going to copy that automatically, e to the power of x. And finally, for our digit 3, there is a restriction. Only the digit 1 is not around. We have also provided that in one of the videos in this playlist. Please just try to review that. If 1 is not around, it's just equivalent to e to the power of x minus 1. So we simply need to multiply all of this, and whatever will be the result later on, express it in power terms, power series in this term, and then later on we will see the corresponding pair of this, because the coefficient here, in this case 1, is our a sub r. Okay, so let's start. Take note, we can factor 1/2 here and another 1/2. I don't want fractions in our FOIL method. So you have your e to the power of x minus e to the power of minus negative x. That's the numerator of the first. The numerator of the second is this one. And still we have e to the power of x and e to the power of x minus 1. Okay. Obviously, that's 1/4. Let's multiply this using FOIL method. We'll actually have e to the power of 2x. Add exponents, right? Then, and at the same time, let's not forget this is actually a this will result to a difference of 2 squares, because we have the same first term, same second term, but opposite operation. So difference of 2 squares. So simply square the first term, square the second term. That's times e to the power of negative x squared by multiplication, so it's e to the power of minus 2x, right? So please take note of that. I'm erasing this. Okay, and then for multiplying binomial expressions with the same first term and the same last term and opposite operations, use minus. So that's why it's called difference of 2 squares. As for this, you have e to the power of 2x minus e to the power of x. Okay, now multiply this again. Now binomial, two binomial expressions. So FOIL method now. So the first, this one and that, it's actually equal to e to the power of 4x. Then outer, this one, you will actually have minus e to the power of 3x, that's 2x plus x. Then you will have this inner terms, so it's actually minus e to the power of 2x, minus 2x plus 2x is actually 0, right? And finally, the last terms, so you're just going to add the exponents, so that's positive, negative times negative, e to the power of minus x. Okay, now I understand this is equal to 1. Okay, but in the meantime, let's not try to make it equal to 1, because what we want is the form of this one here. So how could we get e to the power of 4x, e to the power of 3x, e to the power of 0, and e to the power of negative x? How can we get all of this in terms of a power series? Now here comes the technique. Since our e to the power of x here at the top, okay, I'm going to erase all some scribbles here. E to the power of x at the top will equal to the power series intended for this. If we're going to change this x into 4x, into 3x, into 0, into negative x, we're going to change this x here in the power series into this equivalent forms as well. This will mean this is equal to the summation of 4x to the power of n over n factorial, as n is equal to 0 to positive infinity. Okay, let me remove some of this at the bottom, but the same concept will be followed later on, because we are changing x in the original form into 4x. That's why it's the 4x raised to the power of n. Then, by power law, e to the power of 4x is equal to the summation of 4 to the n, x to the n over n factorial, as n starts from 0 to positive infinity. As you can see, we already have this form. That's this form here. Okay, so the item outside from that, this is our a sub r, 4 to the n. But this is just one of the components. Let's call it a sub r sub 1 for e to the power of 4. Next, let us consider e to the power of 3x. Okay, a similar thing, the summation of 3x raised to n over n factorial, as n starts from 0 to positive infinity. So you have here the summation of 3 to the n, x to the n over n factorial. Okay, n factorial, that's e to the power of 3x. So basically, same thing as earlier, we had this. So our a sub r here, to separate from the first, a sub r sub 2 is equal to 3 to the n. Next, how about e to the power of 0? Okay, here is e to the power of 0. Again, it's just equal to 1, but in terms of power series, so this is actually equal to the summation of 0 raised to n over n factorial as n starts from 0 to positive infinity. So that's actually equal to 0 to the n is just 0 over n factorial, so it's equal to 0. Okay, I told you this is not necessarily equal to 0. It's equal to 1, of course. Any expression raised to any expression, term, variable raised to 0 exponent is actually equal to 1. But in terms of power series, okay, it's equal to 0 here. Okay, so don't be confused with this. Take note of that. Finally, e to the power of negative x is equal to the summation of negative x raised to n. You have here over n factorial as n starts from 0 to positive infinity. So we have e to the power of negative x is the summation of negative 1. We have the negative 1 there raised to n, x to the n over n factorial as n starts from 0 to positive infinity. Again, as mentioned, we had this. So by the way, this was actually our a sub r sub 3, 0. This is our a sub r sub 4. That's actually equal to negative 1 raised to n. Now all of the 4 components are already done. So from here, okay, we know that again, okay, it's here, this one, 1/4. So I'm going to write here 1/4 times the a sub r of e to the power of 4 is this one here. So 4 to the n minus, for e of 3 of x is actually 3 to the power of x is 3 to the n. Then you have here 4 is e to the power of 0 is plus 0, or let's say minus 0, just to follow the operation. And plus, we had this negative 1 raised to n, or simply removing a 0, 1/4, 4 to the n minus 3 to the n plus negative 1 raised to the n. This is what would describe the general form of a sub r for the situation here where we are to identify the number of n-digit quaternary sequences that contain odd number of zeros, even number of ones, and at least 1, 3. Again, we had this form for our answer. So we follow the same process. The critical part here is this, of course. How do we solve that? And of course, this portion here, very critical. You must remember what would be the equivalent if we're talking about odd, even, if except, or at least 1 rather, and if it's just the same. Okay? Thank you very much for watching.